Hi all, this is Mr. Yeager with Continuing Physical Science. Sorry, trying to get that out of the way. And we are looking at finishing up motion. Basically, we've gone through speed and velocity, we went through distance and displacement. Now we are on to acceleration, which I always tell everybody in physics is one of the most difficult terms for people to initially really understand, just because of the initial understanding of what it is from a day-to-day perspective versus what it is in physics, which is actually very, very important in terms of the true meaning behind it. So what we have here is acceleration is a change in velocity over time, okay? Which I think most people kind of understand. They kind of know it's how quickly you are changing your, let me switch colors here again, yep. How quickly you're changing your speed. Okay, oops, sorry about that. But the thing is with it, since we're looking at this terminology, that it's a change in velocity over time. Velocity is speed and direction. Speed and direction, all right? Which means I just need to change one of those in order to accelerate the object. Again, everybody's very hooked to the change in speed, and usually people think it's only an increase in speed means acceleration. But if you decrease in speed, you are also accelerating. I know that we have the word decelerate, but that is a word we don't really use in physics. We just say that you're accelerating in the opposite direction of motion. Okay? So velocity, we can accelerate by changing our speed, increasing or decreasing, but we can also accelerate by changing direction. And this is always the one that's asked about. They love asking about this of how can you accelerate but maintain the same speed? By changing direction. If we change direction, we change velocity. If you recall, we had that one diagram where the car was going around a circular track, and we said while the speed stays the same, the velocity is constantly changing because we're changing direction. That means the object is accelerating. So in order to accelerate, we either change your speed or change the direction, or we can do both. Okay? To actually calculate it, we use the formula final velocity minus initial velocity over time. The symbols for it is VF minus VI over T, final velocity minus initial velocity divided by time. Our units for acceleration is meters per second squared. That's because velocity is meters per second, which then I'm dividing by time, which is in seconds, which leads us to meters per second squared. Again, this is telling you how you are changing your velocity. One of the other things about acceleration is it doesn't actually tell you that it's moving, but it's telling you how it's changing its motion. That's the big thing we're looking at there. Okay? So for physical science, the nice thing is we really just kind of look at it in terms of whether you have positive or negative acceleration. So we do try to make it a little bit more simplified. All right. Basically, you have a positive acceleration if you're speeding up. When you speed up, we're going to say you have a positive acceleration. Okay. A positive acceleration. So we have this one problem here. A airliner starts at rest and at the end of the runway, it reaches a speed of 80 meters per second in 20 seconds. Okay, so how can we calculate that? Well, the initial velocity was 0, the final velocity was 80, all right, divided by 20. 80 divided by 20 is 4 meters per second squared. So that's showing you a positive acceleration where the person is speeding up. If there's a negative acceleration, what we're looking at is the object is slowing down. Okay? So we're going to say speed up is positive, slowing down is negative. Okay? So if you're moving in a straight line at a constant speed of 3 meters per second and you come to a stop in 2 seconds, what is your acceleration? Well, if I stop, how fast am I going? 0 meters per second. All right? So what am I going to do? This is my final velocity. Here's my time. Here's my initial velocity. All right? If I solve, okay, final speed, there you go, 0. Initial speed is 3. We would do 0 minus 3 divided by 20 comes out to negative 0.15 meters per second squared. Make sure you're reading the problem, okay? I have some people that sit there and always just subtract the larger minus the smaller. That's terrible, okay? Be reading the problem and recognize what you're starting with, which is 3, what you're ending with, which is 0. 0 minus 3 divided by 20. We can have a negative acceleration. It just means, again, you're slowing down, okay? So a couple of those quick questions already reviewing. This is a pretty quick section. Acceleration is the rate of change of velocity, okay? It's a rate of change of velocity, okay? It's how quickly your velocity is changing, and you can accelerate by speeding up, slowing down, or changing direction, okay? Which is not a form of acceleration, okay? All right, if we maintain a constant speed and direction, what does that mean? That means we have a constant velocity, which means, am I changing velocity? Acceleration is a change in velocity divided by time. Go ahead and make sure. But even if you just remember change in velocity, that's a change in velocity, okay? So if I maintain a constant speed and direction, am I accelerating? No. This one would be, it is not accelerating. If I speed up, am I accelerating? Yes, I'm changing my speed, my velocity. If I slow down, yes, I'm changing my speed, I'm changing my velocity. If I turn, I'm changing my direction, so that's also accelerating. So which one is not accelerating? A. Okay? A. All right. All right. One more. What is the acceleration of a hockey player who's skating at 10 meters per second and comes to a complete stop in 2 seconds? All right, so acceleration, even though it'll be on the next page, let's just kind of write this out. Vf minus Vi over t. We're solving for A, who is skating at 10 meters per second. There's my initial velocity, comes to a complete stop. That means my final velocity is equal to 0 in 2 seconds, t. What's this going to be? Final, 0 minus 10 divided by 2. Negative 10 divided by 2, it'll come out to negative 5, B. Okay, negative 5, I think we have to work on the next page here. Okay, there you go. So you are slowing down. You know it has to be negative. Okay? All right, just another quick topic that's related with acceleration is gravity. We're going to come back to this a little bit more in Unit 3 on Newton's laws and force. All right? But gravity, what happens is when you are in the air, you are accelerated by gravity. And we call this, you're in free fall. Free fall is when you're simply in the air. When an object is thrown into the air or dropped into the air, the only thing acting on it will be gravity. Okay? Well, it turns out then, how are you going to move? What's going to happen? Okay? Gravity causes an acceleration. All right? It always causes an acceleration downwards. Okay? Always causes an acceleration down. All right? And it's always equal to, the correct answer is it's 9.8 meters per second squared, but you're perfectly allowed just to say 10 meters per second squared. I mean, most people do. All right? So gravity will always accelerate an object 9.8 meters per second squared. What does that mean? It's going to change the velocity 9.8 meters per second every single second. You're going to get, let's make this easy. Just immediately using 9.8. 10 meters per second every single second. So you're going to get 10 meters per second faster if you're going down every single second. You're going to go 10 meters per second slower if you're going up, because if you go up, you're going to slow down. All right? But that's basically what we're looking at. It's going to change. Gravity is an acceleration, which is going to be always 10 meters per second squared acting downwards. So if we had a problem with it, we could continue using this acceleration formula. If you drop from rest an object and it falls for 3 seconds, how fast is this object going? So you're starting at an initial velocity of 0 meters per second. Time is t equals 3 seconds. What's your acceleration? Well, that's where some people might get confused. You've dropped it. So what's acting on it? Gravity. So gravity has an acceleration of 10 meters per second. I'm trying to solve for final velocity. So I'll let the board take care of this. Okay, there we go. Acceleration is 10 meters per second squared. Initial velocity 0. Time equals 3 seconds. Plug it on in. Okay, it would be 10 equals VF minus 0 divided by 3. Well, VF minus 0 is simply VF. So 10 equals VF divided by 3. So I'm just going to multiply the 3 over. You should be going 30 meters per second after 3 seconds. That makes sense. You're going to get 10 meters per second faster every single second. After 1 second, you should be going 10 meters per second if you started at rest. All right. After 2 seconds, you're going to get 10 meters per second faster, so you'll go up to 20 meters per second. After 3 seconds, you're going to change by 10 meters per second, which is now 30 meters per second. Okay? So you're always changing the same amount. Some people get that confused where they're like, oh, it doubles, and they go 10, 20, 40, 80, and so forth. That's wrong. It's always changing, accelerating 10 meters per second every single second. All right? It gets that much faster every single time. All right. We will see this also, like I already said, next unit some more. Gravity accelerates all objects exactly the same. If there's no wind resistance, which basically that's how we kind of do it. If there's no wind resistance, no air resistance, a giant object will fall just as fast as a smaller object. Okay? I mean, we always use just some ridiculous idea like an elephant and a mouse. If they both fall through the air, they're both going to fall at the exact same rate. A lot of people will think the elephant's going to fall faster. It won't. Gravity pulls on both objects equally at 10 meters per second squared down. Okay? So there's a video here of the moon drop. Basically, what they're showing there is on the moon, there's no air resistance. So the astronaut in Apollo 15 basically has a feather and a hammer and drops both of them at the same time, and they actually both hit the ground at the same time. You would think the feather would fall more slowly, but if there's no air resistance, gravity pulls everything down the same. All right, that is it. Thanks.